Take 8. I kid you not. I am having major problems with video. So hopefully this one works. Oh boy, oh boy, oh boy. Okay, so this video is meant to reinforce what you did the other day in terms of learning about the EM spectrum and how we collect information about the EM radiation that the universe gives off and what we've learned about the universe by analyzing this information. So, what you should have with you is your ESRT, something to write with. And if you were able to, your printed notes. If you were not able to print the notes, that's fine, really. Just have a piece of paper. You could write your answers on the piece of paper. All the questions will be on the screen. You can just write your answers on a piece of paper. Okay? So, what is EM energy and how is EM energy radiated through the universe? Well, electromagnetic energy, also known as EM energy, also known as radiation, also known as the EM spectrum, also known as light or EM radiation. When you think of light, you think of light that you can see. Like right now, it's the sun's out. Oh, turn on the light, something like that. Astronomers think of light as all the wavelengths. So from gamma rays to radio waves, they just call it light sometimes. So that's interesting that they think of the whole spectrum as light. Unlike that's not how we think of it, but that's how they think of it. Okay. You already learned about what the EM spectrum was, so we're not going to watch this video. That's fine. Let's take a look at this graphic, though. All right. This graphic is really cool because it kind of puts all the information about the EM spectrum in one place. So as you can see down here, the hotter the temperature of the body that's emitting the wavelengths, okay, the more energetic the radiation. So you need really, really hot, energetic bodies, things in space like supernovas to give off gamma rays because it's very high intensity radiation. The lower the temperature, the less intense the wavelength, the less intense the energy of the electromagnetic radiation. So it gives you these um, objects to think of the wavelength, how long the wavelength is. Okay. Here are all the types of radiation, but this is where I want to focus right here. Do the wavelengths penetrate the Earth's atmosphere? Yes or no, or sometimes that's gray. Radio waves, yes. That's how we communicate with our spaceships, with the space station, with the men who went to the moon, with the Voyager spacecraft that's right now sailing out past Pluto, with the Mars rovers. That's how they got their information back to us on Earth. Microwaves, yes, sometimes some wavelengths do. Infrared, some do. Visible, definitely. Okay. Ultraviolet, some do. That's how you get sunburnt. Okay. X rays and gamma rays do not penetrate the Earth's atmosphere. Thank goodness, because they are harmful to us, right? Okay. Here's another graphic. There's a question here. What is the relationship between the frequency and the wavelength of EM radiation waves? Well, very long wavelength radiation, like radio waves, have a frequency of about 10 to the sixth. About 100,000 of these pass by every second. But lower wavelength radiation, 10 to the 21st, pass by us pass by a point every second. So as the wavelength of the electromagnetic radiation increases, the frequency decreases. So it's an inverse relationship. All right. Okay. So now we're going to focus on visible light. And remember that it's Roy G. Biv, red, orange, yellow, green, blue, indigo, violet. Sometimes you're going to see indigo and violet combined because our eyes can't really make out the difference between indigo and violet many times. All right, so you might see Roy G. Biv instead of Biv. Okay. And the band of colors is called the visible spectrum. Now, in the old ESRTs, there was actual data. So you could be given a certain wavelength and determine what color it was or what type of EM radiation it was. We don't have this. You just have this. So all you have to know is, hey, as I move to the right on this graphic, the wavelength is increasing. As I move to the left on this graphic, the wavelength is decreasing. And here we have the little sliver of visible light. Okay, violet, blue. Note there's no indigo. Violet, blue, green, yellow, orange, red. If you look at red, outside, if you follow this line up, just outside of red is infrared. Makes sense, right? So let's go to violet. Let's follow this line up. Just outside of violet is ultraviolet. So that makes sense too. So if we're shifting to the left here, we're blue shifting, not violet shifting, blue shifting. Our wavelength is getting shorter. If we're moving to the right here, we're red shifting. Our wavelength is getting longer. Okay, and there's like a nice rainbow with a lighthouse there. It's pretty. Okay, So telescopes, why do we use telescopes? To gather more data than our eyes can, to magnify the images. And we use telescopes to collect all parts of the EM spectrum. Um, you may not think of telescopes as collecting anything else but visible light, but they do. They collect everything. All right. So where do we put them to get the best data collection? Mountaintops, above the clouds, above the air pollution, to minimize the atmosphere's distortion and refraction of the EM waves. Dry climates, less moisture means less clouds. Remote areas get away from light pollution. And the best of all, put them in space. Cut out the middleman. Get rid of the atmospheric refraction and awful stuff that it does. Also, why can't we put telescopes that collect gamma rays, X rays, and ultraviolet waves on the ground? Because those waves don't penetrate, remember? Okay. Does visible light penetrate the atmosphere? Yeah, we have lots of telescopes down here. Some infrared does. Okay, so we can collect it in planes, but we have telescopes up there too. And do radio waves penetrate the atmosphere? Yeah, some do. So we have radio telescopes down here. But if we want to collect all of these wavelengths, we need to put them in space because the wavelengths won't come through. Excuse me, won't come through our atmosphere. Okay. So here's a really nice graphic of lots and lots and lots of telescopes that NASA uses to collect this data. So for gamma rays, you're going to use Hess, Fermi, and Swift. There's Swift, Fermi, and Hess, right? For X-ray, Chandra and NuSTAR. Ultraviolet is Galix. Visible, you got Kepler, Hubble, whoop whoop, Keck 1 and 2, SALT, Gemini for visible light. You got Spitzer, Herschel, and Sophia plane. That's the plane to collect infrared. You also have Gemini North. That's also infrared. That's down here with Gemini. You have for microwaves, Planck and Karma. And for radio waves, you have Spectre R, Green Bank. And you also have the Very Large Array, the VLA, which you're going to see a picture of in a little while. And these are radio telescopes. So just to show you the difference between earthbound collection of data and space collection of data, this is a beautiful photo of the Orion Nebula from the Kitt Peak Observatory in Arizona. This is the same nebula collected with Hubble. So you can see the difference in the quality and the clarity of the image. Earthbound, Hubble. So this is why we put telescopes in space. One reason we put telescopes in space. Now this is current events. On May 8th, this image of Jupiter was taken. They used combined images from 3 different telescopes. They used infrared images from Hawaii's Gemini North Telescope, optical images from Hubble, and radio images from the Juno Space Telescope to get this image. And this shows you the different temperatures of the area of Jupiter underneath the clouds. That's the benefit of using infrared. You can see through things, literally. Okay, so that's kind of cool. All right, so when we think of optical telescopes, we think of those typical telescopes that you look through. Sometimes it's a straight line. Sometimes you can look through at a 90-degree angle to see the images. All right. Hubble is 30 years old. There's actually a really good 2-hour special on the Science Channel right now that tells you all about the history of Hubble and its repair missions and the data that it's collected over the years. It's like my favorite. There's a new telescope that's going to come out in 2021. It's called the James Webb Telescope. And that telescope is going to be launched and go beyond the moon. And it's an infrared telescope. There's a picture of Hubble. This is the Webb. It has multiple layers of metal shielding to protect it from the heat given off by the sun and the earth, so that this antenna can collect only infrared heat from space, not from us. So it wants to look further back in time than Hubble did. All right, into space. Okay, radio telescopes have collected a lot of data for us over the years. It's like a giant satellite dish that collects the data, concentrates it, and sends it to the computer to analyze it. This is the Very Large Array. All of these radio telescopes act as a unit to focus and concentrate the signals that they collect. That's the Very Large Array at night. They can change the pitch of them with the motors. Okay. This is also a radio telescope that's in Puerto Rico. It's called the Arecibo radio telescope, and it's 3 football fields across to focus and collect those signals. And it's also seen in the James Bond movie GoldenEye. All right. So that's a bunch of information about how we collect the data. But when they collected this data, what do they do with it? What have they determined about distant stars and galaxies? Okay. So when they collect visible light, they use a spectroscope to separate it into its component parts. All right. When we want to know properties of elements, we can use instruments to measure mass and volume and determine their density. We can use controlled experiments with thermometers to determine their melting points and boiling points. We can use the Mohs scale to determine their hardness. We can use all these instruments to determine their properties. Well, a spectroscope allowed scientists to determine another property of elements. When elements are heated to the plasma state, so solid, liquid, gas, plasma, when the elements are heated to the plasma state, they give off light. All right. The light that they give off has a certain pattern, it has a certain spectral line pattern. All right. So it gives off different wavelengths because of their electrons, and that's chemistry and physics, and you'll study that in the future. Okay. But when we heat the elements to plasma state, this is what they give off. They give off, these are called emission spectra, or spectral line patterns of the elements. So this is another version of the periodic table. So here, this box is hydrogen's box on the periodic table. When hydrogen is heated to the plasma state, these are the wavelengths that it gives off. This is its spectral line pattern, its fingerprint. This is helium's fingerprint. This is beryllium's fingerprint. This is lithium's fingerprint. Okay, let me show you another model. Okay, this shows you the symbol of the element and its spectral line pattern. Okay, so again, what this is you're taking the element, you're heating it to the plasma state, and you're looking at it with a spectroscope. And these are the patterns that you're getting. So if you see this pattern, you know that you have germanium. If you see this pattern when the element is heated to plasma, you know that you have aluminum. Here, magnesium, etc., etc. Okay? So when we look at a star that's the plasma state, or a galaxy that's a bunch of stars in the plasma state, we can determine what elements we're seeing by studying the light and breaking it into its component parts. So here's hydrogen, sodium, helium, neon. Neon lights in the pizza window are red. Makes sense. Mercury, iodine, and argon. Some of the lights in the pizza window are filled with argon gas, not neon gas, so they're going to look bluish purple, not red. All right. So let's say a star is made of hydrogen and helium. Hydrogen and helium. You're going to have both of these patterns combined. But all we have to do is look for those patterns in the pattern, in the combined pattern, and we can determine what's in it. All right. So here's a question about that. Given the bright line spectra of 3 elements and the spectrum of a mixture formed from at least 2 of these elements, which elements are present in the mixture? So here's the spectral line pattern of element D, here's the pattern of E, and here's the pattern of G. Here's the pattern of the mixture. Which element spectral line patterns can you see in the mixture? Okay, so let's check out element D. Okay, that line is accounted for. That line is there. That line's there, that line's there, that line's there, and that line's there. It looks like element D's pattern is in this mixture. Can you tell me if E and G are present in this mixture? Pause the video and figure it out and pick the best choice. Okay, so you should have determined that element E's lines are present in the mixture, but element G's lines are not present in the mixture. So the correct answer is element E and D only are present in this mixture. Okay. So there's different types of spectrum. You don't have to worry about this. We would have done this a little bit more if we were in school. Okay. There's continuum spectrum, bright line spectrum, and absorption spectrum. Don't worry about it. Here's where it's coming to, the Doppler effect. Okay. These line patterns can shift depending upon if the star or galaxy is moving away from us or closer to Earth. All right? The movement of spectral lines toward the red side or blue side of the EM spectrum tells us if a star or galaxy is 1, moving away from us or towards us, 2, the speed at which they're moving, and 3, the distance they are away from us. Okay? So, the Doppler effect. If the police car is moving toward you, the sound wave gets compressed, or if the police car is moving away from you, the sound wave gets stretched out. Let me show you a graphic on this. Here's a spectral line pattern from the laboratory that we've determined this is the property of the element. This is the element at rest. It's not moving towards us or away from us. If you see the spectral line pattern moving all the way over here towards the red side, it's moving away from us quickly. If it's shifted over here, it's moving away from us slowly. This is coming closer slowly or coming towards us quickly. Okay? It's at rest, moving away from us slowly. Oh, if it's shifted all the way over there, it's moving away from us quickly. Now, why is this? The red side of the EM spectrum has a longer wavelength, so it's getting stretched out. The blue side of the EM spectrum has a shorter wavelength, so the wavelengths are getting compressed because it's moving towards you. Okay, so let's go back here. Okay, if the lines of the object spectrum have shifted towards the red side of the spectrum, it shows the wavelengths are getting longer. So here's a galaxy. It's moving away from us. The light that the galaxy is giving off, the wavelengths are getting stretched out. That means this is the baseline of the pattern. They're shifting to the red side. The further the shift, the faster it's moving away from us. Here's us on Earth. Okay, now here's another one. This galaxy is moving towards us. So the light that it's giving off is getting compressed. Shorter wavelength. It's moving to the blue side of the spectrum. It's blue shifted. And the greater the shift, the faster it's moving towards us. Okay, so here is the laboratory spectral pattern of an element. This is unshifted. You see how all the lines move towards the red side? And not only that, but the pattern remained the same. So the space between each line is consistent. So we still know what elements the light is made of. It's just the whole pattern moved as a unit to the red. Of course, here, the whole pattern moved as a unit to the blue. So we don't compare it to this. We don't compare it to the red shifted pattern. We go back to the original, the unshifted pattern, and compare it. Okay? So here's what we're going to do. This is the laboratory spectrum. This is the lines at rest wavelength. So this is whatever element has this pattern. Okay? Well, here is the same exact pattern, the same space between the lines, but it's red shifted. So object 1, if the lines have red shifted, the object is moving blank us. The object is moving toward, the object is moving away from us because it's getting redder. The wavelengths are getting longer or stretched out. Now, object 2 is a greater redshift. Okay, so if you look here, that's lab. This is redshift. Whoa, that's a lot of redshift. This object, object 2, object is moving away from us faster than object 1. Okay, so object 1 is moving away from us, but object 2 is moving away from us faster because there's a greater redshift. I want you to pause the video and I want you to use that thinking to talk about object 3 and object 4. Object 3 is blue shifted, object 4 has a greater blue shift. So do that and we'll come back. Okay, object 3, the object is moving toward us. Good. And object 4, greater blue shift. Object is moving towards us faster than object 3. Okay, so that's how redshift, blue shift works. Okay, now, what did we learn about the universe by studying all these spectral line patterns? This guy right here, this is Hubble. This is Edwin Hubble. That's who the Hubble telescope is named after. He discovered a lot. Okay, what was the observation that he made? In the 1920s, he looked at blobs in the sky that everyone else believed were to be nebulae that were located within our Milky Way galaxy. And he proved that these blobs were not in our galaxy. Rather, they were other galaxies. Because everyone pretty much up until that point thought that the universe was our galaxy. That everything in the universe was within our Milky Way. Okay? This proved that the universe existed outside of our Milky Way. It's a new observation that he substantiated with evidence. So then, when he looked at all these galaxies, he noticed a very interesting phenomenon. The vast majority of the galaxies he observed and measured had spectral line patterns that were, spoiler alert, redshifting. So he said, oh, that galaxy's redshifting. That galaxy's redshifting. This led to universal expansion. Okay? He also proved that the galaxies that were further away from us were moving away from us faster than galaxies that were closer to us because they had greater redshifts. This observation and this conclusion was the basis of the formulation of the Big Bang Theory. Okay? So all the galaxies are moving away from us. That proved universal expansion. What could have created universal expansion? A really big explosion. Let's call it the Big Bang. Okay? The Big Bang Theory is the dominant scientific theory about the origin of the universe. Okay, basically, there was a teeny tiny ball of matter. All the matter in the universe was compressed into a teeny tiny little space. Don't ask me. I don't know how that can be. But approximately 13.77 billion years ago, plus or minus 59 thousandths of a billion, the universe was created from a cosmic explosion that hurled matter outward and in all directions. Radio telescopes are still hearing, quote unquote, the leftover noise from the Big Bang in the form of cosmic microwave background radiation. They can still hear the leftover rumblings from the Big Bang. How cool is that? Okay, now, how do we know the age of the universe? Well, the Wilkinson microwave anisotropy probe, the WMAP, collected the cosmic microwave background radiation from the universe and mapped it. And by mapping this cosmic microwave background radiation, they were able to measure the age of the universe. And that's where the number on this slide comes from this map. How cool is that? All right. And we think that scientists believe that this is pretty accurate. All right. So the Big Bang Theory came from the observation of all the redshift. Okay. The universe is getting larger. Everything's moving away from each other. Okay. This redshift in the vast majority of the galaxies and stars that we observe is the proof that the universe is still expanding. All right. So when the Big Bang occurred, hydrogen, some helium, matter, and dark matter were created in the moments after the Big Bang. That's where all of us come from. All right. So this is a graphic of the Big Bang. Scientists hypothesize that at the very beginning, the ball of matter was extremely hot, 10 to the 32nd degrees Kelvin. It's crazy hot. And what's been happening to the temperature as the universe has been expanding? Well, right now, the average temperature in the universe is about 3 degrees Kelvin. So as the matter expands, the temperature is decreasing. Okay. And you could think of the Big Bang as the galaxies moving away from each other as like coins taped to a balloon. If you inflate the balloon, the space between the coins is increasing, but the coins themselves aren't increasing. Okay. So the galaxies aren't getting bigger. The space between the galaxies is getting bigger. So that's that. Now, this is the Hubble Deep Field photo. You're going to watch an Edpuzzle video that explains how this was made. All right. And every single blob in here, every single speck is an entire galaxy, not a star. So what we're looking at is actually a photo of the past. All right. So let's say this galaxy is 10 billion light years away. Okay. The light that entered Hubble's lens left this galaxy 10 billion years ago. So this is actually a picture of the past. So every time you look up in the sky at night, the starlight that's entering your eyes left that star, however many light years away from us it is, which is pretty cool. So how did it get this photo? Hubble, this is Hubble right here, looked into the cosmic past. All right. And so all this light that entered Hubble's lens left those galaxies that many million years ago. All right. Webb is designed to see past this, to see into the infrared, because all of this light has now shifted so far to the red that it's now in the infrared part of the electromagnetic spectrum. So they're hoping that Webb can look further back than Hubble. Hubble can only see invisible light for the most part. All right. So that's my spiel. You're going to watch an Edpuzzle video, and then you're going to answer some questions about redshift, blue shift. All right. Take care, everyone.